Welcome to video lecture E4. This one is on reduced echelon form. I'll be your educator, Tom Roby, and here are the outline and objectives. What we'd like to do now is to systematically use row operations to compute the unique reduced row echelon form, RREF, of a given matrix A. We've already seen the definition of this, but I'll remind you of it again. The difference between echelon forms by themselves are already useful, and sometimes they're good enough. But what's particularly nice about the row-reduced echelon form is that there's a unique one associated with every matrix. So if you and somebody across the classroom from you try to compute echelon forms, you might actually get slightly different answers. They would have to be related to each other, but they could be different. But if you both compute the row-reduced echelon form, you should get the same answer unless one of you made a mistake. And then we'll see how to use the row-reduced echelon form to easily analyze the solution sets to systems of linear equations. So let me just write down the definition on this early slide because it takes a lot of space. So a matrix, and this is really a reminder, it's in reduced row echelon form if it satisfies all the non-zero rows are above any rows of all zeros. So if you look at this picture, you'll see that we've got a couple of rows of all zeros, two rows of all zeros at the bottoms, and the rest, the stars mean you could have any non-negative, any non-zero or possibly zero entry in it. The leading entry is always in each non-zero row is a 1. Okay, so if you look across, you see, okay, you go to there's zeros, and then you get to a 1. Bunch of zeros, and then you get to a 1. If you look in the column of one of those leading entries, you'll see that everything else is a 0. So the idea is that you can use that 1 to then zero out all of the entries both below and above in that same column. And finally, echelon means staircase in French. And so this echelon form means that these ones sort of come in a kind of staircase shape. So the leading one in each row is in a column to the right of the leading ones above it. Okay, so this is the same as the previous definition. It's just written a little bit more cleanly so that I only have to write 4 things. So this is meant to be a generic matrix in row-reduced echelon form, except that there are mistakes in it. So where are the mistakes? Why is this not satisfy? What conditions here are not being satisfied? So pause the video for a minute if you like and figure out why this is not a matrix in row-reduced echelon form. Okay, so why is it not in row-reduced echelon form or reduced row echelon form? Notice that in this row, I've put they're non-zero entries here. These stars indicate possibly non-zero entries, but the first non-zero entry in each row by 2 has to be a 1. So that means that I either have to make this a 0 and this a 1, and then this has to be a 0 as well, or I could make this one a 1, and then this has to, and if I make this a 1, then these two have to be zeros. Okay, so let's see. Let's suppose I make this one a 1. So if I make this one a 1, I correct that to be a 1. Then this one has to be a 0, right? Because everything in that same column with the 1 has to be a 0. But it's okay for these. Oh, and then this is the first entry, so then this guy also would have to be a 0. Okay? But I could still have this entry be any generic number, 3 or -7 or square root of pi or whatever. Okay? So now I've corrected that defect. There's one other defect. Do you see where it is? Right, if you look all the way over to this antepenultimate column, column 8, you'll see that there's this 1 here, where we call these things by the way, these are often called pivots. So this pivot could be used to zero out all of these entries without changing anything else in the matrix. And in fact, that's what you have to do if you want it to be in row-reduced echelon form. So that means that this has to become a 0, this has to become a 0, this has to become a 0, and this has to become a 0. Okay, in order for this to be a row-reduced echelon form matrix. So as I often say, they're deliberately planned mistakes to make sure that everybody's paying attention. And now I'm pretty sure that if you check all of these conditions carefully, you'll find that it's all okay. Actually, another thing you could have done, if you'd wanted to leave those things as stars, you could have just killed this row. You could have killed row 5, and then you would have had a matrix that was in row-reduced echelon form. Or you could have made row 5 a row of all zeros, but then you would have had to move it below this row, which is a non-zero row. You would have had to move it, say, to the bottom, and then you would have had a row-reduced echelon form matrix without having to change these stars to zeros. So there's more than one way, but the point is once you get into row-reduced echelon form for any given matrix, that's going to be unique. Okay, so the main difference between ordinary echelon form and row-reduced echelon form is that the leading entries in echelon form didn't have to be 1s, but now they always have to be 1s. And you always have to, in echelon form, you could have had things like these stars above the pivot, but now you can't have that anymore. Now you have to have all of those things are zeroed out. So above, if you look in any row that contains a 1, that's the only non-zero entry in that column, in any spot. Okay, so here's another definition. A pivot position of M is a location of a leading 1 in row-reduced echelon form of M, and a pivot column is one that contains a pivot position. Okay, so going back here, we see that, okay, well, we've got these pivot positions are here, 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 and here, and then the pivot columns are just the columns that those are in. So the other columns are, so the pivot columns here are columns 1, 4, 5, 6, 8, and 9. Okay. And now let's take a look at some smaller examples that are easier to tell. So here, I'm not going to do, so in a lot of the future lectures, I'm just going to assume that you know how to do the row reduction, and I'm not going to show you all the steps anymore. So this matrix row reduces, and if you're using software, this is what you would get. You would just go straight from here to here, and the point is, how do you interpret it? So in this situation, when we look at the row-reduced echelon form, we've got a 1 in every column in every row. And so this is, so there are 3 pivots, and every column is a pivot column. On the other hand, if we took this example, then we find that we get a row of all zeros at the bottom, and there's a pivot here, and there's a pivot here, but no pivot in this column. So there are 2 pivot columns, 1 and 3. And in this situation, there are pivot columns, as you can see, in 1 and 2. Right? So you could call these guys the pivot columns in the original matrix, and that would be fine, because the pivot columns don't change when you do row operations. All right, so here's a new definition, but the same set of 3 examples. The basic variables are the ones that correspond to the pivot columns. So all 3 columns are basic variables here, x1, x2, and x3. In the second example, x1 and x3 are basic variables. In the third example, x1 and x2 are basic variables. The other variables are called free variables, and they're the ones that are going to let us have infinitely many solutions when we set things up. So here, there are no free variables. Here, there's 1 free variable, x2, and here, there's 1 free variable, x3. And just, to think about what that means in terms of solving the equation. So if I want to solve this system of equations, it's clear what happens, right? I have a unique solution that says x1 is equal to 2, x2 is equal to 3, and x3 is equal to -1. 3 basic variables, no free variables. Here we get an equation where this will say, maybe I should write this down. So maybe let me just write this down quickly. So x1 equals 2, x2 equals 3, x3 equals -1. Whereas in the next one, what happens? Well, this one says that x1 equals -2x2 plus 9. The second equation says that x3 equals 3. And now this x2 is free. And what that means is that if I substitute any value that I want for x2, I could call it t if I wanted, then x1, if x1 is -2x2 plus 9, then, and x3 is equal to 3, then that will always be a solution. So I can get solutions like, well, if I let x2 be 0, then x1 would be 9, x3 is always 3, but another possible solution would be x3 always has to be 3, but if this were, say, 1, then this would be 7, right? So those are two different solutions, and there's a whole one-dimensional line of solutions. Okay, now down here, we get similar things. So if you wanted to solve this one, you would get that x1 equals negative 2x2 negative 2x3, and x2 equals negative 3x3 plus 1, and x3 equals, actually we don't get x3, right? We get 0 equals 1. So in this last situation, we see that we get an inconsistent system. So there's no solutions here, even though we have a free variable, right? So in one situation, we have a free variable, and it means we've got infinitely many solutions. In another situation, we have a free variable, but because the system's inconsistent, we actually get no solutions. Okay, so finally, let's actually do a whole problem from scratch. So let's write the parametric description of the solution set for this system of equations. And so I'll do the whole thing out for you. So first of all, notice that this corresponds to an augmented matrix. What's that augmented matrix? Well, it looks like it's going to be 0, 1, 2, 3, 2, 0, minus 6, minus 8, 3, 6, 3, 6. Okay, and now if we do send it to row-reduced echelon form, what happens? Well, you'll end up I guess we'll divide this by 2 and move it up, so we'll end up getting 1, 0, minus 3, minus 4, and then we'll have 0, 1, 2, 3. And you'll notice actually that if you add these guys in the third row, you'll actually get 0, 0, 0, 0. Okay? So this is an equation where we get a row of zeros. We have two pivot columns. So pivot columns are 1 and 2. So the basic variables are x1 and x2, and we're going to write those in terms of, so the free variable is x3, and we see that when we write down the system of equations that this represents. This boils down to saying that x equals 3x3 minus 4, x1, and this one says that x2 is equal to negative 2x3 plus 3, and then 0 equals 0 doesn't tell us anything. So what does that mean in terms of finding a solution? Well, so this implies that if I'm looking what x, y, oh, whoops. I used x, y, z over here, and I switched to x1, x2, x3 over there. So I'll just rewrite this as x equals 3z minus 4, and y equals minus 2z plus 3. Okay. So now I'm back over here. So x, y, z is equal to 3z minus 4 minus 2z plus 3, and then z is equal to z. And now you just factor out a z from this. And think about this as the well, first I guess I'll write this as negative 4, 3, 0. Right? This is just the sum of two vectors. And then 3z minus 2zz. And so that's minus 4, 3, 0 plus z times 3 minus 2, 1. Okay? So now, so this is what you might call a parametric form of the solution, where this is a solution where z can be any real number that I want. And so it's always good to check your answers in your original equation. So according to this, one solution should be minus 430, right? So what happens when I plug minus 430 in here? Well, let's see. Then I'm saying that 3 plus 2 times 0 equals 3, check. And then here I'm saying that minus 8 is minus 0 is equal to minus 8, check. And then for the last one, I'm saying minus 12 plus 18, so that's 6, plus 0 equals 6, check. So it works. So minus 430 is a solution. If I want to be really careful, I should check that I didn't make a mistake in this vector. Actually, when I was working this example out, I did make a mistake, and I caught it by double checking. So according to this formula, if I add 3, negative 2, 1, or 2 times it or whatever, to negative 430, any multiple of this, I should get another solution. So let's just check. So minus 430 plus 3, negative 2, 1 should also be a solution, and that's equal to negative 1, 1, 1. Okay, so let's check now that when we plug negative 1, 1 in here that we're good. So if both of these guys are 1, then I get 1 plus 2 is 3, check. If this is minus 1, and I get negative 2, and this is plus 1, I get negative 6, so those add to negative 8. And now if this is negative 3 plus 6 is plus 3, plus another 3 is 6. Okay, so this one is also a solution. And this procedure for solving a system of equations is quite general. It works all the time. I guess we've already seen that. But it's nice to do it in row-reduced echelon form, in particular because that's something that you can feed to your favorite calculator or computer software package. Say, what's the row-reduced echelon form? And from that, you can easily figure out the rest of this to determine what the complete solution is. So that's it for video lecture E4. Thank you for your kind attention.